Day-to-day symptoms of COVID-19. Before proceeding, please note that this general overview is compiled for initial self-assessment only and may vary for each individual. If you are not feeling well, you should immediately consult a medical practitioner to have an accurate diagnosis and proper treatment of COVID-19. The typical daily symptoms are concluded from the study of 138 patients at Zhongyang Hospital of Wuhan University, and another study involving 135 patients from Jinyintan Hospital and 56 patients from Wuhan Pulmonary Hospital. These symptoms are broken down into Day 1 to Day 2. The beginning symptoms are similar to the common cold, with a mild sore throat and neither having a fever nor feeling tired. Patients can still consume food and drink as usual. Day 3. The patient's throat starts to feel a bit painful. Body temperature reads at around 36.5 degrees Celsius. Although it's uncommon, other symptoms like mild nausea, vomiting, or mild diarrhea are possible to set in. Day 4. Throat pain becomes more serious. Other symptoms like feeling weak and joint pain start to manifest. The patient may show a temperature reading between 36.5 degrees to 37 degrees Celsius. Day 5 to 6. Mild fever starts. The patient show a temperature reading above 37.2 degrees Celsius. The second most common symptom, dry cough, also appears. Dyspnea or breathing difficulty may occur occasionally. Most patients in this stage are easily feeling tired. Other symptoms remain about the same. These 4 symptoms are among the top 5 key indications of COVID-19, according to the final report of the initial outbreak conducted by the Joint Mission of China and WHO. Day 7. The patients that haven't started recovering by Day 7 get more serious coughs and breathing difficulty. Fever can get higher, up to 38 degrees Celsius. Patients may develop further headache and body pain, or worsening diarrhea if there's any. Many patients are admitted to hospital at this stage. Day 8 to 9. On the 8th day, the symptoms are likely to be worsened for the patient who has coexisting medical conditions. Severe shortness of breath becomes more frequent. Temperature reading goes well above 38 degrees. In one of the studies, Day 9 is the average time when sepsis starts to affect 40% of patients. Day 10 to 11. Doctors are ordering imaging tests like chest X-ray to capture the severity of respiratory distress in patients. Patients are having loss of appetite and may be facing abdominal pain. The condition also needs immediate treatment in ICU. Day 12 to 14. For the survivors, the symptoms can be well managed at this point. Fever tends to get better and breathing difficulties may start to cease on Day 13. But some patients may still be affected by mild cough even after hospital discharge. Day 15 to 16. Day 15 is the opposite condition for the rest of the minority patients. The fragile group must prepare for the possibility of acute cardiac injury or kidney injury. Day 17 to 19. COVID-19 fatality cases happen at around Day 18. Before the time, vulnerable patients may develop a secondary infection caused by a new pathogen in the lower respiratory tract. The severe condition may then lead to blood coagulation and ischemia. Day 20 to 22. The surviving patients are recovered completely from the disease and are discharged from the hospital.
Assalamu alaikum. I am Nazmur Shoaid, lecturer in physics, Boshell Cadet College. Due to corona pandemic, you will stay home. We think that you are safe and sound in your home. Inshallah, we will meet soon. Today I discuss that is chapter number 8. The name of this chapter is Periodic Motion, and today is the first class of periodic motion. By the end of today's class, boys, you must be able to know about periodicity. Number 2, periodic motion. Simple harmonic motion. Number 4, characteristics of force for simple harmonic motion. Differentiation equation of simple harmonic motion. Energy of a particle executing simple harmonic motion. So no more delay. Firstly, I discuss periodicity. Periodicity is the event that repeats itself regularly in space and time. If you look these pictures, you more understand about the topics. A pattern of periodic, if it can be represented by specifying a finite portion of it and the duration of each repetition. Periodicity can be classified into two categories. One is spatial periodicity and other is temporal periodicity. Firstly, I discuss spatial periodicity. First, boys, you look the pictures. There is the lattice and the space between the atoms in a solid substance. The distance between all the atoms are equal. Now I discuss spatial periodicity. When a repetition of an object or motion happens with repeat to position, that is a space, it is called spatial periodicity. For example of spatial periodicity, button in shirt, electric pose, atom in crystalline solids, etc. Now I discuss temporal periodicity. Firstly, you look the two pictures. Both of the pictures depend on time. So temporal periodicity must be related to time. When repetition of an object or motion happens with respect to time, it is called temporal periodicity. Earth motion round the sun, the motion of a hand clocks, motion of a rocking chair are the example of periodicity. The rotation of the earth around the sun is periodic and its time period is 365 days. This periodicity is expressed as y is equal to sine theta. Now I discuss periodic motion. First, you look at the pictures. All of the pictures are in motions, and this must be related with time. A motion of a body or particles that repeats itself over and over again after a regular interval of time, it is called periodic motion. This interval of time is termed as time period. The periodic motion of a body can be linear. You see here, this is a linear motion example, and circular. This is the example of circular or elliptical. This is the example for elliptical. The motion of Earth rotation around the Sun, the motion of electrons around the nucleus, the oscillation of a pendulum, the motion of a mass suspended from a coil spring are example of periodic motion. If the motion of a body is periodic motion, that's back and forth over a same path about its mean position. As you look here, this is the simple pendulum, this is the equilibrium position, and this body suspended from this equilibrium position to A and B, same interval of time. So this is a on kind of example. Then the motion is known as oscillation or vibratory motion. The oscillatory motion is therefore a periodic to and fro, that is forward and backward motion. One complete to or fro motion is called an oscillation or vibration or a circle. The number of complete oscillation or cycles in unit time is called out frequency of vibration. Now I discuss simple harmonic motion. It is the simple kind of periodic motion of oscillatory nature. If the acceleration of a particle in a periodic motion is always directly proportional to its displacement, that is called x, from its equilibrium position, and is always directed towards to its position, then the motion of the particle is said to be simple harmonic motion. This motion can also be classified into two kinds. One is linear simple harmonic motion and another is angular simple harmonic motion. So I firstly discuss the first portion, that is linear simple harmonic motion. This is the example of linear harmonic motion. Now I discuss what is linear simple harmonic motion. The motion is said to be linear simple harmonic motion if the displacement of a particle executing simple harmonic motion is linear. The example are the motion of simple harmonic pendulum, the motion of a point mass tied with a spring is the example of linear simple harmonic motion. Now I discuss angular simple harmonic motion. If the motion is said to be angular simple harmonic motion, if the displacement of a particle executing simple harmonic motion is angular. The example of angular simple harmonic motion are transitional oscillations and oscillation of a component or compound pendulum. Now I discuss the characteristics of simple harmonic motion. The motion is periodic, oscillatory, and linear. Acceleration is proportional to its displacement. Acceleration is opposite to the displacement. Acceleration is directly towards the mean position. At any position of the mass, total energy remain constant. Simple harmonic motion can be expressed as sine or cosine function. So boys, if you write this equation, y is equal to r sine omega t or a sine omega t, or y is equal to r cos omega t, or y is equal to a cos omega t, that's depend on you. Now I discuss the differentiation equation, that is differential equation of simple harmonic motion. We know from the Newton's second law of motion, F is proportional to minus x, and we know that F is equal to ma. So ma is equal to minus kx, and we write this equation, that is ma plus kx is equal to 0, then a is equal to, that is a plus k by m into x is equal to 0, and we know that the differential mode of acceleration A is equal to d square x by dt square, and this is the another phase of acceleration A. If we differentiation 2 times of the displacement x, then it's convert to acceleration A. And we know the equation of acceleration from this equation. A is equal to minus k by m into x square, and we know the relation between angular acceleration uh, or acceleration and angular velocity omega, that is A is equal to minus omega square into x. So the comparison of the both equations right hand side, we can write that omega is equal to k by m. So now we put the differentiation mode of acceleration and the values of k by m, that is omega square, in this equation. We get the differentiation mode or equation of simple harmonic motion is d square x by dt square plus omega square x is equal to 0, and the another look of acceleration x differentiation mode of 2 times plus omega square x is equal to 0. So this is initial angular velocity, and we write this equation omega naught, and this is final angular velocity, that is omega. If there are no difference between initial and final, so we can write that omega naught or omega. So finally the differentiation equation of simple harmonic motion is d square x by dt square plus omega naught s square into x is equal to 0. Now I show you the solution of simple harmonic motion. Previously we discussed f is proportional to minus x, that is acceleration A is proportional to minus x, and we know the relation between angular and linear acceleration and angular velocity. A is proportional to minus omega square into x, and we know that the differentiation mode of acceleration A dv by dx into dx by dt, and we know that dx by dt is a velocity, so v is equal to dx by dt. So now we put the values here, dv by dx into v. So acceleration A is equal to v into dv by dx, and this is also minus omega square into x. Now I integrate this equation with the separation of velocity and displacement x. Integration of 0 to v into dv is equal to integration of 0 to x minus omega square x into dx, and we know the values of this integration. Here we use the formula x to the power n. So we know that x to the power n plus 1 by n plus 1 is the result of this integration. So ultimately result of left hand side is v square by 2, and the right hand side omega minus omega square is a constant, so x square by 2, and plus 1 is the integration constant. Now our work is to find out what is the values of this integration constant. For solving this kinds of problem, we put a limitation or limit in this equation. We know that at maximum displacement, that is called A, the velocity will be 0. Now we put this value here. and ultimately we get the constant value C is equal to omega square into A square by 2. If we value B is equal to 0 and X is equal to A, we must be find out the values of constant C. Now we put the values of constant in the main equation. We get the ultimate result V square by 2 minus omega square into x square by 2 plus omega square into A square by 2. Now we write that V square is equal to minus omega square into x square plus omega square into A square, and V is equal to root over omega square into A square minus x square. And we know that the differentiation mode of velocity v is equal to dx by dt. Now the separation of displacement and time t, we get the ultimate result dx by root over a square minus x square integration, and is equal to integration of omega into dt. And we know that the values of sine inverse x by a is the result of integration of dx by root over a square minus x square. So we write that sine inverse x by a is equal to omega is a constant, so dt's integration is t, so omega t plus phi is another integration constant. And finally we can write from this equation x is equal to a sine omega t plus phi. So this is the solution of simple harmonic motion. And previously I said that it's a sine function or cos function. So if you write here x is equal to a cos omega t plus phi, this also be right. And using this equation I show you some problems. The problems are to find out potential energy and kinetic energy. We know that the potential energy U is equal to half of kx square. Now the values of x, that is x is equal to a cos omega t plus phi. Boys, you must careful here. Now I put the values of x is equal to a cos omega t plus phi, because uh, you may flexible to put sine function or cos function. So the ultimate result of potential energy half into k into a square cos square omega t plus phi. And now our turns to find out kinetic energy, and we know that the equation of kinetic energy half mv square, and we know that if we displacement uh, put in the differentiation function, now we find out the values of velocity v. So the equation of velocity v is equal to dx by dt, and if we differentiate the displacement, then we find out the values of omega square, that is v square. So the values of v square is equal to omega square into a square sine square omega t plus phi. And we know that omega square is equal to k by m. So k is equal to m into omega square. So now we put the values here. Then ultimately the values of kinetic energy half into k into a square sine square omega t plus phi. And the conservation of energy, we know that total energy at any position, it must be constant, and we know that the total energy equation is equal to K plus U. Now we put the values of potential energy and kinetic energy from these equations, and E is equal to K plus U. So we put here half into K into S square is a common function, and the values of cos square omega t plus phi plus sin square omega t plus phi, and we know that the cos square plus sin square, that is cos square theta plus sin square theta, is equal to 1. So the ultimate result of total energy is equal to half into K into A square. But you must careful here, the total energy is always time constant. So at any position, the sum of potential energy and kinetic energy is must be equal to half into K into A square.
Boys, now I discuss 4 MCQ type questions. Number 1. Which one of the following is not necessary for simple harmonic motion? Question for A. Elasticity, B. Inertia, C. Restoring force, D. Gravity. Question number 2. What is the phase difference between displacement and velocity in simple harmonic motion? Option A 0, option B pi, option C twice pi, option D first pi. Question number 3. What is called the length from the point of suspension of the center of mass of the bob of a simple pendulum? Option A amplitude, option B angular amplitude, option C time period, option D effective length. Question number 4. What is the time period of a simple pendulum at the center of Earth? Option A 0, option B infinity, option C equal to Z, option D equal to effective length. Now I show you some knowledge based question of today's lesson. Question number 1. What is periodicity in physics or physics? Question number 2. What is an example of periodicity? Question number 3. What is the law of periodicity? Question number 4. What is periodic motion? Question number 5. What is simple harmonic motion? And I only show 2 comprehension based questions. Question number A. Why simple harmonic motion is called simple? Question number B. Why is true simple harmonic motion rare in nature? Now I give you a home task. That's one kind of creative questions. A block with a mass of m1, that is first mass m1, 5 kg, is sliding to the right with a speed of 15 meter per second when it's hit and stick to a block of mass m2, that is 3 kg, attached to a spring of a spring constant k is equal to 3000 Newton per meter. The second block was the equilibrium position and the spring uncompressed at the time of the collision. The horizontal surface is frictionless. Question number A. What is simple harmonic motion? Question number B. Explain Hooke's law. Question number C. Find the maximum acceleration of the joining blocks. Question number D. If add extra 2 kg for the first body, then what will be change is coming in the acceleration of the joining blocks. And lastly, boys, if you have any query, please write in inbox. And I think you are safe and sound in your home. With this hope, I'm Nazma Shwet. Thank you. Thank you all.
A very interesting point about a simple harmonic motion is that It can be considered as a projection of a uniform circular motion. That is, a uniform circular motion, when viewed sideways, is a simple harmonic motion. We can also consider a simple harmonic motion to be a shadow of a uniform circular motion. Let us say that the angular speed of a particle moving along a circular path of radius a is equal to omega. If the particle starts from this position, then after time t, its angular displacement will be equal to omega t, and this distance x will be equal to a sin omega t, which is in fact the equation of an S.H.M. As omega is a measure of the angular displacement per second, so omega can also be considered as the angular frequency in the context of an S.H.M. If instead of starting from this position, the particle starts from such a position, then the position of the particle after time t will be equal to a into sine of this angle, that is omega t plus phi. This angle represents the phase constant of a simple harmonic motion. When we say that two simple harmonic motions have a phase difference of phi, this means that their corresponding circular motions are separated by the initial angle phi. For the phase difference of pi by 2, the situation is as shown. If one S.H.M. starts from the mean position, then the other S.H.M., which is ahead by a phase of pi by 2, will start from the extreme position. That is, if this S.H.M. follows a sine function, then the other will follow a cosine function. This is evident if we write phi equal to pi by 2 in this equation, because then this term will be equal to cos omega t. Similarly, a phase difference of pi will be like this. In general, the graph of an S.H.M. that is ahead by a phase phi can be obtained by shifting this graph towards left.